a um, uh, next lecture, which will be a week from today, we'll begin with Ben de Carte doing some hands-on demonstrations of the code in the GitHub site, which I think has been quite active, and I'm very pleased about that, because a really big motive for me in all of this is to get other people using what I think are these very useful tools. Another thing, at the end, the question came up last time, what do I mean by closed form? It's actually a little hard to say. If you want a lengthy exposition, go to the Wikipedia entry, but roughly speaking, it means a formula, an algorithm, if you like, that uses the familiar arithmetic expressions, right? The multiplication, division, addition, subtraction, exponentiation, finding roots, the trigonometric functions, and so on. Practically, it means using just the functions that are built into all the scientific programming languages, and in fact, not all of those. I mean, it wouldn't include, for example, the Bessel function, but let's say all the well-known functions that are built into the science programming languages. It's at least as important to know what it isn't. So any algorithm that uses loops, iterative solution, searches for a solution. So the nonlinear curve fitting functions, for example, are not closed form. They do gradient descent. And in fact, if you want sort of the opposite of a closed form algorithm, it's any algorithm that does a gradient descent. So backpropagation, for example, is an extreme example of a non-closed form thing. And they involve orders of magnitude more floating point operations when you execute them. So the closed form expressions are low energy, fast, efficient, whatever. With that, I'll go on to a come on. Went on Zoom. There we go. So we're going to do information today, and information is tossed around all the time in cognitive science and neuroscience. But it's very unclear what people actually think they mean by it in many usages. Prior to Shannon, it was already very much in everyday usage, but it wasn't a scientifically useful concept. And now, of course, it's the foundation of information technology and also much of modern physics. We wouldn't be doing this without Shannon's definition of information, because it pointed the way to highly efficient codes that are crucial to the internet. And the central concept, Shannon's definition of information is entropy. And the entropy is the measure of the uncertainty in a distribution. Now, the first very counterintuitive thing about it is another term for the uncertainty in a distribution is the available information. Okay, so already you say, well, wait a second. I think intuitively, uncertainty is more or less the opposite of information. If I'm well informed, I have little uncertainty, and that's right. I mean, Shannon's approach captures that intuition. But it's very important in what follows to bear in mind that uncertainty and information always refer to the same quantity, and the technical name for that quantity is entropy. So the entropy of a distribution. So information is a property of a distribution. One way to ask us to sort of test mentally is, are they serious when they're talking about information, is to ask yourself, what distribution are we talking about here, right? If we're talking about information, we must be referring to a distribution. So the start of the definition of entropy is the definition of surprisal. And again, here, this is very intuitive. I mean, the less probable something is, the more surprising it is, right? So Shannon's definition of surprisal is it's the log of 1 over the probability. So as the probability here gets small, of course, its reciprocal gets large. So as probability goes to 0, something that's extremely improbable, the reciprocal here goes to infinity, and the log goes to infinity very, very slowly. Why the log, you might ask? Well, we want surprisals to be additive. That's if one thing is surprising and another thing is surprising, the amount of surprise should just be the sum of the surprises, right? And that leads, whoops. That leads to the definition of entropy, which is just the average surprisal. And the formula for that, there's various forms for this, but this is the one I like. So here's the entropy on the left, and it's defined by this sum. And it assumes we have a vector of probabilities. Remember, a probability distribution consists of 2 vectors, a support vector and a probability vector. So now we're working just with the probability vector of some distribution. And we go through all the elements of that probability vector, and for each element, we compute the log of the reciprocal of that element, and we weight it by the probability itself, and we add them all up, and that's the entropy of the distribution, the average surprisal. I think it's, at least for me, it's somewhat instructive to notice the similarity between the definition of entropy and the similarity, but also the difference. And the definition of the other things we're familiar with about distributions, their mean and their variance. Right, this is perhaps not the form in which you're most used to seeing it, but this is the way one computes the mean of a distribution. You notice that you step through all the elements of the support vector, and you multiply each element by the probability to which it maps, and you sum those weighted, the probability weighted support things. And similarly for the variance, you step through all the elements and you look at their deviation from the mean, which you calculated here. Again, you weight it by the probability and so on. The key thing here is to notice that these measures that we define on a distribution involve both the probability vector and the support vector when you're computing them, right? Whereas this one involves just the probability vector, okay? The support vector does not enter into the computation of the entropy, whereas it does for the mean and the variance. This is a purely practical matter. When you get into doing this numerically, and if you start doing this stuff seriously, you sooner or later you'll end up doing some of it numerically. There's an important practical thing you need to know, which is that the surprisal, as the surprisal goes to infinity, it goes slowly. Where I already pointed out that when p goes to 0, right, 1 over 0 goes to infinity, right? So this, and so does its logarithm. So as p goes to 0, surprisal goes to infinity. However, remember the key expression is the log. Have I already gone over? No.
Some people should turn off their microphone because there are some.
Okay. So this is going to infinity slowly, and this is going to 0 fast. And so the expression as a whole goes to 0 as pi goes to 0. And you need to know that when you start doing numerical work, because you're looking at this distribution and many of them are countably finite. Countably infinite, like the geometric, for example, or the Poisson. And you say, well, how many, I can't do an infinite vector,
Benim için
right?
kusura bakma ya böyle.
How many elements of this
İşten
vector?
kafam güzeldi. Sordukça da anlattım ben. Sıçtım yanınıza, özür dilerim.
Somebody has a microphone on. How many elements should I include? And the rule of thumb is, well, make the plot and just, of course, distributions always rise above the x-axis and then fall back onto the x-axis. And you only include the values that lie beneath the distribution, right? Where the probability is non-trivially greater than 0. Now you must say, well, what do you mean, Gallistel, non-trivially? Well, it depends on how anal you are, right? I mean, one definition of non-trivial is, well, what's the maximum p in this distribution? And then if we go down to 1,000-fold lower than that, that's non-trivial in some people's books. If you're more anal, then you can say, let's go down to 1,000,000-fold, whatever. The amount of computation goes up as you go down, but that's the practical advice. Now, it's really important to realize that the computation of this is laughably trivial in any modern scientific program, right? I mean, here it is in MATLAB. We have a vector of the p-values for the distribution we're interested in. This expression in MATLAB, the dot and the asterisk, defines element-wise multiplication, right? So we have here the vector of p-values. Here we have the vector of the log of the reciprocals. We just multiply them element-wise, and that gives us the entropy. In nats, well, in MATLAB, this would be the natural log. And in MATLAB, if we want it in bits, we do the same thing, but we use log2 and we get it in bits. Again, in doing this, you have to ask, well, how long is my vector of p going to be? That is, you have to think about what are the plausible values for my vector of p values. In making any plot, of course, you have to make such a decision, right? You're never going to have a plot with an uncountable infinity of p values. You're always going to say, oh, I'm going to make some set of p values and then plot them. All right. So the definition of entropy is completely unproblematic as long as we're dealing with discrete distributions. And to look kind of far ahead here, a sort of take-home message is, at the end of the day, we're actually always dealing with discrete distributions because of limits on precision and so on. But nonetheless, in what's to come, one needs to understand that there is a problem with the definition of entropy for continuous distributions. And Shannon himself saw very clearly there was a problem, but he thought he could finesse it, and he was more or less right, although he wasn't as rigorous as modern ways of approaching this. But all we need to understand is, what is the problem? So notice that for the discrete distribution, it's defined as a sum. Okay, when we go to a continuous distribution, instead of a sum, we have an integral. But if you remember your calculus, a question immediately arises, well, does our integral converge? That is, when we start summing over infinite things, maybe the sum goes off to infinity in itself, in which case it's not well defined, right? It's not a number that we can work with for most purposes. The essential problem is that the integral, when you replace the sum with the integral, it doesn't converge. And you can see that practically just in this example. So I have here exactly the same two exponential distributions, right? And later on, we're going to want to look at the differences in these entropies. So up here, the solid line up here and the one down here, they're exactly the same exponential distribution. And ditto for, you can't even see that this is the dashed line. But here in plotting this, I've discretized it, both distributions, much more finely than I have down here, right? I have a cruder distribution down here. I've only used 25 values down here, whereas I've used 100 values in computing the entropy of these distributions, both down here and up here. Okay, so what's the entropy of the distribution up here? It's I have one is with a mean of 8 and one was a mean of 16. And the entropy with the mean of 8 up here is 4.4 whatever, and 16 is 5.4. The exact same computation down here, but just more crudely discretized, gives values of 2.4 and 3.37, right? Whoa, that doesn't look like this sum is converging, right? And in fact, you can go on doing this, and every time you increase the number of points up here, this integral goes up. And it never does converge, it goes right off to infinity. So the entropy isn't well defined. And Shannon himself pointed this out in the original paper, but he said, look, what we're pretty much most of the 99% of the time, we're really interested in the differences in the entropy, right? We don't care about the entropy of 8 or of 16. We only care about the difference. And if you look at the difference, you say, oh, look at that. It looks like the difference is converging, right? I mean, here it's 0.9718, and here we discretize more finely, and it's only very slightly greater. And if you keep this up, you see, yeah, it's really converging. Okay, so the difference, this is hard to get used to, but that's why calculus is sometimes counterintuitive. The difference in entropies is well defined and of a continuous distribution. And so for most purposes, that's good. But you'll see that this issue comes up again. And in the paper, oh, I forgot to mention. So these lectures are based on a paper that Peter Latham and I are working on. It was posted earlier, an earlier version of it, which was sort of a disaster. It was basically before Peter laid his hands on the draft that I had made. And Peter's a vastly better mathematician than I am, and tidied things up enormously and phrased things better and so on. So the old draft has been replaced by a new draft, and I urge you very strongly to, if you've downloaded the old draft, get rid of it, download the new draft. It's clearer, it's better, it's cleaner, the notation is more consistent, blah, blah, blah. Trying to make there we go. Okay, that brings us to another. So entropy is one foundational measurement in quantity in information theory, and the other, there are really two foundational measurements. And the second one is the relative entropy, which is also called the Kullback-Leibler divergence. And here's the formula for that divergence. So let me walk you through this. So here's the standard expression for the Kullback-Leibler divergence over on the left. And it's a divergence between, it's a measure of the extent to which one distribution differs from another distribution. But it's called a divergence, not a measure, because very importantly, as we'll see in a moment, the divergences are not symmetric. That is, the divergence of P from Q is not the same as the divergence of Q from P. So you can't think of it as a distance, it's a divergence. And that's very important to bear in mind. Okay, so the capital P and the capital Q refer to distributions, right? And the formula for this is, again, very simple. So P sub X here is is one distribution on X, and Q is another distribution. And again, you should think of these as vectors of probabilities. All right. And again, notice that only the probabilities come into play. The support doesn't come into play. So you take over here, you're taking the ratio of each probability in this vector to the corresponding probability in this vector, right? They're defined, corresponding means having the same support, okay? So you take the log of all of those ratios and you weight each, so now you've got a whole vector of logs of these ratios and you weight it by the vector of probabilities. So again, it's an average, right? It's a weighted sum. And that's the Kullback-Leibler divergence. Some information theorists consider this more basic than the definition of entropy because this is well defined even for continuous distributions. This, here the integral converges. Now again, probably the most important thing to bear in mind is that this can be radically asymmetric. So just to illustrate that, here's the suppose we have one Bernoulli distribution with a p-value of 0.99 and another distribution with a p-value of 1. You say that's a distribution? Well, yeah, sort of. It's an extreme case, right? Okay, what is the divergence between, I mean, the intuitive, you say, well, gee, they're pretty close, right? And indeed, when you compute the divergence, putting the 0.99 here in the first argument and the 1 in the second, you get 0.01 bits, right? But what if you turn it around and put the 1 in the first argument and the 0.99 in the second argument? Try it in MATLAB. Now MATLAB says, well, that divergence is infinite. Now, intuitive, this makes, when you think about it, this makes total intuitive sense. Okay. Suppose I tell you, I tell you all almost all swans are white. Right? 99 out of every 100 swans are white, right? And you say, no, it's not almost all, it's all swans, right? So I think it's 0.99, you think it's 1. Well, how many swans are we going to have to examine before we settle the argument, right? Well, even if we got to 1,000 swans, right, you wouldn't be persuaded. You'd say, oh, no, just keep going. We're going to come across. Anyway, you can see that it's going to take a hell of a lot of swans to solve. Now, suppose on the other hand, we turn it around, right? How many swans do we have to look at to say, whoops, there are black swans, right? Well, the answer, the expected number is just 100, right? So we will know with absolute certainty. The evidence will be infinite. And the reason I'm going through this is we're going to be using this as a measure of the strength of the evidence. And when we run it this way, we expect that we will have infinite evidence after 100 observations on average. Whereas here, basically, we'll never get to infinite evidence, or we'll need infinite observations. So it's entirely intuitive. And of course, the same thing applies if we have 0 and 0.01, right? Okay, the practical importance of this is that when you start to use this, you have to think to yourself, okay, which distribution do I regard as the Q distribution and which do I regard as the P distribution? And in all the work that I'll be reviewing with it, the Q distribution is always the reference distribution, and the P is a distribution that may or may not differ from the reference distribution. And I'll be referring to this reference distribution in many different ways. I'll call it the marginal distribution. I'll call it the contextual distribution when we get to associative learning. and so on. I should stop at this point. Are there any hands raised? Any questions, Virginie? We keep in mind, we're going to have a half an hour of discussions if I mind my time. Whoops, I got to go faster. Okay, hang on.
There's none. You still have a few minutes.
Okay, but I'm running out of time here and I'm just getting to the most important part. Okay, the mutual information, which is often just called the information, also called the information gain, is the average amount of information about X that one gains from observing a Y, right? So it arises when two variables are not independent, right? And the math, it's defined in many different ways mathematically, each illuminating in its own right. And it's denoted by I, X distribution, semicolon, Y distribution. Again, the capital letters here indicate distributions. And one is, it's defined using the Kullback-Leibler divergence. It says that it's the Kullback-Leibler divergence of the joint distribution from the P given Y from the cross product, the joint distribution here. I'll be illustrating this in a moment. Another distribution, another way of defining it, which is more intuitive, I think, is that it's the sum of the two marginal distributions. Again, I'll be illustrating this momentarily. So the entropy of one marginal distribution plus the entropy of the second marginal distribution minus the entropy of the joint distribution. And finally, we come to the form that I'll be using a lot. These are all equivalent definitions that can be shown to be identities. It's the entropy of a marginal distribution minus the entropy of a conditional distribution. So let's hasten on to the okay. So now we see, here's to try to make what I'm just saying, which I imagine was fairly confusing. I hope now clearer by using the scatterhist command in MATLAB to show both a joint distribution, which is just a scatter plot that we're all familiar with, and the so-called marginal distributions, which you just get by taking, it's just, with Zoom, EndNote behaves very oddly. And now I have to, what do I do here? Okay, there you go. Now I'm trying to go back. There we go. Okay. Let me unpack this some more. So remember, it's the information that you gain about X, or as it turns out about Y, by knowing a value for the other one. So think of it in terms of horizontal slices through this distribution, right? So when we make a slice like this, we're looking at all the different values of X that we observe when Y equals very close to 0. Okay, that's what all these points are, right? Whereas if we make a slice up here, we're looking at all the different values of X on that's down here, that we observe when Y is equal to 20. Okay. Now it may not, if you look at this, or sort of squint at this, you can kind of see that the distribution will be the same for all different values of Y. It thins out as we get here, but you notice that the scatter is covering roughly the same amount of territory, regardless of what the value of Y is, right? So that tells us that we learn essentially nothing about X by knowing the value of Y. And similarly, if you imagine slices along this axis, right? So now what do we learn about y from knowing the value of x? Well, again, if you squint at this, you're saying, it looks like practically nothing. And in fact, these were completely independent distributions that I used in making this scatter plot. So in fact, the amount of mutual information is vanishingly small. This is just small sample error. It's actually 0. And so, and when we divide the mutual information by the entropies, the marginal, we get a contingency of 0. We can come back to this in the questions, because I think I'm almost done. And I hope this becomes even clearer when we look now at when they're not independent, right? So how did I generate these artificial data? Well, I imagine a kind of trace conditioning experiment in which there's a beep every now and then. It's randomly distributed in time with a mean of half a second. So in the end, the distribution is going to be 11 seconds mean. So the US, and this beep warns that one is about to get a reinforcement, like a shock or a bit of food. Now, usually when one runs this kind of experiment, the latency to the reinforcement, the gap between the beep and the reinforcement is fixed. But I want, in which case the distribution has 0 entropy. But I wanted to have some residual uncertainty. So I made the gap an exponential distribution in its own right, but with a very much shorter mean. So intuitively, when you hear the beep, you know the US is coming. It's coming pretty quickly, but there's a little uncertainty about exactly how quickly. Okay, so if you just look at the distribution of the beeps, that would be on the y-axis. That's what's going to be the CS later. This is the marginal distribution of the beeps. This is the marginal distribution of the US's, the bits of food or the shocks. And this is the joint distribution. And the contrast between this and what the previous joint distribution is the visualization of what information is all about. Mutual information is all about, right? You take, now when you do the slices, you say, oh, wow. When I know what the value of X is, I have a very accurate idea, not a completely accurate, but a very accurate idea of what the value of Y is. And vice versa, when I know what the value of Y is, yeah, there's a little jitter in what X is going to be, but it's quite minor. Okay, so the entropy of this distribution is what we mean by one marginal entropy. This is the other marginal distribution and its entropy. And you can see that the conditional distribution or the joint distribution now has very little entropy. It's the entropy of the residuals, right? These modest deviations between this line. So in this case, you would get a great deal. There's a lot of mutual information between Y and X, which means that learning the value of a Y greatly reduces your uncertainty about how long you're going to have to wait for the next X. Okay, I think that's it. Yep. So discussion. I'll leave the slides up. Questions?
I'll ask a question while people think a bit about what you presented. Can you perhaps go back to the KL divergence, the Leibler difficult? Yeah. At some point, you say that you wanted to use it as a measure of evidence. Can you perhaps explain which? So you mean a measure of evidence in the context of empirical work, and in which case, how do you choose which is the P and which is the Q? distribution in your example.
Right. So, yeah, so that that's where we're headed. Okay. But so let me say something about this. So, first of all, this has the same units as entropy, right? That's why it's sometimes called the relative entropy. Okay. And it crops up in many different uses in information theory, but here's where it's going to crop up. For me, the huge importance of this is that it comes from Shannon's coding theorem, which is where we're headed in the next lecture. What this measure, suppose, sorry, the trouble is that to answer your question properly, I have to cover some things I haven't yet got to, right? And most particularly Shannon's coding theorem.
I can be patient and wait for the next.
Well, I think redundancy, your question leads to one of the, to me, most important things in the whole series of lectures. So, and I'm sure some redundancy on this part is going to be useful, and also will give people the time to think of further questions while I babble on about this. So Shannon's coding theorem says that to save the most, so modern technology depends upon highly efficient codes. That's what underlies Zoom and everything we're doing now, is the bit patterns that come off of our microphones are uncompressed. They're not efficiently coded. But then the program takes those bit patterns, it takes that information and recodes them in ways that use many orders of magnitude fewer bits. And that's what makes it possible to transmit what we're saying in real time. And the same applies to the images, right? That's what makes it possible to transmit our images to each other in real time. So when you're using an inefficient coding scheme, ASCII is an example of an inefficient coding scheme, right? ASCII assigns an 8-bit word to the 256 different characters you can produce on a usual keyboard, a standard keyboard, right? Well, some of those key characters you use 100 times a day, and some of those characters you might not use once a year. So it's obviously wildly inefficient to use 8 bits for each character, right? And Shannon says, yeah, it sure is. And you can devise a more efficient coding scheme in which, and this is not rocket science, right? What do we want here? Well, we want the high probability, the high frequency things, the things we're going to have to send over and over again. We want the code for them to be very short, very few bits. And we want the code for the things that we will almost never send to be very long, or relatively very long, right? And Shannon said, yeah, that's spot on. That's sort of intuitively obvious, but he went on to show that the maximally efficient code arises when the lengths of the words are proportional to the logarithms to the logarithms of the reciprocals of the probabilities. Where have we encountered that? That's the surprisal, right? So the log of the word you use to encode some datum the length of that word should be proportional to the log of the surprisal of that datum. What does that mean? That means, well, if it's very surprising, we're going to encode it very seldom, and so we can use a long code word, and so on. Okay, that establishes the notion of an efficient code and the fact that there is a limit on how efficient a code can be. Now, when you're in, what we're going to be doing here is saying, well, if we change the distribution that we expect, and that's what we just saw with those scatter things, when you go from the distribution, the marginal distribution to the conditional distribution, you say, whoa, that's a big change in the distribution. And that tells you that, yes, it is. And if you're using an efficient code for the marginal distribution, when you now use that same code to encode data that come from the conditional, the joint distribution, you will be wasting memory and channel bandwidth, right? You will be encoding things very inefficiently. And this measures how inefficient you are. This gives you the average number of bits of memory that you will waste if you encode the P distribution using the efficient code for the Q distribution. Okay, so if you use the ASCII code, if we create a really efficient code for the keys on the keyboard, right? To do that, we will need a ton of data on how often people bang the different keys, right? But once we have that distribution, we can construct a maximally or nearly maximally efficient code, right? Now, suppose instead of using that code, we use the ASCII code, right? Which is nice and easily understood, but horribly inefficient, right? We will be wasting a lot of memory. And this tells us just how much memory we will be wasting. Now, I hope that the neurobiological implications of this are fairly obvious, right? I mean, if you believe the brain has memory, I sometimes think, there is no memory in a neural net. So some people seem to think the brain has no memory, but if you think the brains contain memories, then an obvious issue is, well, just how efficient are those memories? And one of the things it tells you is that if something very surprising happens, that strongly implies that you should revise your code. And if you revise your code, you should recode the data that you've already stored in memory, right? In the light of what you've learned from this very surprising event. I hope that resonates with people, reconsolidation and so on, all these memory phenomena that imply that we're constantly going back and revising our memories. Well, this, in my worldview, is the key to understanding why a rational brain would always be doing that, right? It would always be improving its code in order to save its memory resources, use less memory for the same data. And as a hugely beneficial byproduct, there's a theorem that says the more efficiently you encode the data you already have, the better you can anticipate the data you haven't yet seen. So you get two huge benefits. And so this measures how much one distribution differs from another. Now, when you come to associative learning, that's, if you think about it, that's basically what associative learning is about, right? When the CS comes on, it tells you that, what you can otherwise expect in this context has just changed, right? You're going to get shocked. Usually it tells you that you're going to get shocked more often. Sometimes in inhibitory conditioning, it tells you they're going to get shocked or food reward less often. But in either case, it changes the distribution of weights for reinforcement. And this measures the size of that change in a neurobiologically interesting way. And this any measure of the amount of information you get from something is a measure of the strength of the evidence. And so this can be converted to p-values And Latham has derived the very simple, surprisingly simple formula that convert this quantity, this measure, to a p-value. In my mind, the only reason for doing that is sociologically. Most of us know what a p-value means, right? You know, when you say P0001, you say, oh, wow, that's really significant. And we understand that that means, whoa, there's really compelling evidence here for a difference, right? Well, I think it won't happen in my lifetime, but I think by the time some of you have grandchildren, we won't use p-values anymore. We'll say that's significant at the 8-bit level. You'll say, oh, wow, that means that you get really a huge amount of information from. So we will understand that. So that's my answer to your question, and we will revisit that. If that went by a little fast, don't worry, we'll revisit exactly those issues in the coming lectures and show that they apply to understanding real data from associative learning paradigms.
Please go ahead, do ask your question. Thanks.
I think I may be confounding the terms, but when we use surprisal, I mean, if we know something's probability is 0, there's not much surprise in there either.
No, there's
Like
infinite. No, on the contrary. If you believe that the probability is truly 0, if you believe that it's impossible, right? That's what you believe, right? So think about the Einstein's general theory of relativity, right? And the Eddington experiment, right? In the physics up to Einstein's day, that light should bend was impossible. Any physicist would have told you, no, look, we know that cannot happen. Right? Well, Einstein's theory said, no, it must happen. And you should be able to observe it under carefully chosen circumstances, right? And so Eddington set off to where it was, South America, I think, to see whether it was true. Okay, so the light did bend, right? Okay, so when technically the surprisal was infinite. It wasn't 0, it was infinite. Okay, but what does that mean? Well, when surprisal is infinite, it means that something's wrong with our model of the world, right? If our model tells us that the probability is 0, and in fact we observe a black swan, then we know that there's something wrong with the model.
I meant like we expect nothing to happen and nothing happens. In that terms, there's no.
Oh, I see. Well, okay, so that's a really nice question. Let's see whether how I can show you how these various things link up. So one of the really cool things about Bayesian parameter estimation is, remember, when we estimate the intervals between events using the Bayesian, the Jeffreys prior, right? Which has that really weird 0.5, half an event before we've seen any data, right? Your question highlights why we would want to do that, because suppose because it gives us a probability distribution on the rate or the expected interval when we've not yet observed anything. And if you think about it, you say, well, not observing anything is informative in its own right. Yes, I mean, that's what your question brings out, is that if we expect nothing to happen in the next hour, right, and nothing does happen, that says, well, we have a good model. That it says that our rate parameter is very low, and on that assumption, nothing should happen in the next hour, right? Suppose we say, oh, well, the train isn't going to be here for it isn't going to arrive until this afternoon, and it's now 9 in the morning, and the train arrives at 9:05. You would revise your model of the, right? You would say, what, well, wait a second, that's a huge surprise, right? Under the model that we were given, the probability of that is extremely low, right? So wherever that model came from, it wasn't a good model, right? Whoever said that didn't know what they were talking about, all right? Or there was something they didn't understand about the state of the world. And the reason your question is so good is that in associative learning, it's all about, well, how long do you expect things to go with nothing happening, right? Generally speaking, in excitatory conditioning, in that context, in the absence of the CS, you think, well, nothing's going to happen, right? And then when the CS comes on, you say, oh, now something's going to happen, right? So it changes your expectations about how things are going to happen. Now, I need to make one thing clear in saying that. So typically in an associative learning experiment, a Pavlovian conditioning experiment, think Rescorla 1968, right? You put the animal in the box, the noise is going to come on unpredictably. And if you're in the experimental group in Rescorla's experiment, when the noise comes on, you're going to get shocks. And when the noise isn't on, actually, he varied this. He varied the probability that you would get shocks when the noise wasn't on. In some conditions, it was 0, right? But in others, there was some probability. So the expected weight for shock changed in the presence of the CS, except in his truly random control, right? Which was actually the group of greatest interest in the whole experiment, because in that group, you got shocks independent of the CS, right? Okay. No matter what group you were in Rescorla's experiment, I asked Rescorla this. He and I were colleagues. I said, Bob, those rats didn't want to be put in that box. He said, oh yeah, big time. He said you had to be careful or they'd bite you. Okay, they didn't want to be put in the box, even if they only got shocked during the CSs, right? Because when they're in the box, they know, those damn CSs are going to come on and then I'm going to get shocked. So they had an expectation simply from being in the box. And that's why they didn't want to be put in the box. All right. So the real contrast, as we'll see, is the change in expectations between the expectation you have simply from being in the box. If you're in the box, you know you're going to get shocked. And the expectation that you have when the CS comes on. All right. And in all those cases, this is in this paper that John Gibbon and I wrote in 2000 for the Psych Review. If I remember, one of the headings said, what happens when nothing happens? And the people who study timing knows that the brain is very busy making calculations when nothing happens. And the theory of associations really hasn't come to terms with that fact, that there's a lot of information in the intervals when nothing happens. And what we're doing says, yeah, and we can measure that information, the amount of information. That's the, suppose you've been there an hour and nothing has happened. Well, with your Bayesian parameter estimation, you have a posterior distribution on the on that, and that distribution has an entropy, and that's what you've, if you like, learn from being there an hour with nothing happening.
Thank you.
You see the duality between information and uncertainty, right? You've gained information, but on the other hand, the lower the rate parameter in an exponential, the greater the uncertainty, right? So you've gained information, but on the other hand, you think, geez, I wonder when the bus will get here, right? Oh, if you've been waiting for a bus and it's been an hour, right? Well, you've learned the buses don't come every 2 minutes. But now you're wondering, how long can I sit here and wait for that bus, right?
If there are no other questions for today's lecture, or even from previous ones? So we'll be roughly an hour if we start now.
People should feel free. I know often one doesn't, the questions only arise when you're thinking about something after a while. You're saying, where's he? That doesn't quite make sense. I think most of us who lecture have that really unpleasant experience of that happening to us in the middle of a lecture where we think we understand it, we're busy explaining, and then all of a sudden what we're saying doesn't make sense even to ourselves. So it often takes quite a while before you say, wait a second, there's something I don't understand here. And it's extremely useful to me to get feedback from people about what I see. That Peter Coyle has a question here, by the way, Virginie. So let's have Peter come in with his question.
Yeah, could you comment on the entropy of fading expectation?
Well,
in other words, as the conditioning response fades because there's been no reinforcement.
Yes, as we will, I'm not sure I'll get that far, but the information theoretic way of thinking about things gives the only explanation that I'm aware of that actually accounts for the data on extinction as following partial reinforcement. And the answer was sort of implicit in my response to Bill Gahan, the previous question. If you have a certain rate that you expect based on your previous experience, if you expect the bus to come on average every 2 minutes, and you've been there an hour, obviously you have fading expectations, right? And as I pointed out, actually, thank you for this question because it's perfect when I think about it. Okay, so imagine the exponential with a rate parameter of 1 every 2 minutes, right? So it falls, it's telling you that, hey, 10 minutes, boy, it's really bad luck if the bus hasn't gotten here within 10 minutes after you arrive at the bus stop, right? By the time you get to an hour, something's wrong, right? The bus had a flat or whatever. The world has changed, right? And this Kullback-Leibler divergence, because you now have an estimate on the rate parameter given your recent experience that tells you that the rate parameter that applies now is extremely unlikely to be the rate parameter that you thought applied when you arrived at the bus stop, right?
Exactly.
And the Kullback-Leibler divergence says, yeah, it's 15 bits unlikely, and that's astronomical. If you convert that to a p-value, that's astronomical, and that's telling you the world has changed. Again, this is very intuitive. You know, if you've been there an hour, you're beginning to think, well, Jesus, I don't know, maybe the bus isn't coming today, right? I mean, you're not going to sit there for 48 hours at the bus stop when the bus was supposed to come in 2 minutes. And again, that's part of the reason I'm so excited about this stuff, is it quantifies all of those intuitions, right? So that's a very good way to think of fading expectations, is exactly the way to think about the Kullback-Leibler divergence. Putting that as the time goes by, your posterior distribution is changing and it is beginning to diverge very strongly from the distribution that you had. And those distributions are in effect your model of the world. It's what you base your behavior on, right? How long am I going to sit here?
Well, thank you for your comment. Perhaps the rats would think differently if
No, go on. Go on.
Perhaps the rats would think differently if they were put in a box and never got a shock again. But after a period of time, they'd have a fading expectation of a shock.
That's exactly true. And brings us back to Rescorla. So do you know the Rescorla experiment 68 that I'm talking about? It's his it's his most famous experiment. It got him admitted to the National Academy of Sciences at the age of 40, which for a psychologist is unheard of. Oh boy, I'm going to describe it in the subsequent lecture in detail, but it relates back to what I was just saying to the previous question. So he had these different groups of rats, right? And all of them were going to get shocked when they were in that box. But for some of them, they were only going to get shocked when the noise was also present, right? And the noise came on unpredictably. Now, at the end of his experiment, his crucial thing is that he wanted to test their reaction to the noise. And he was measuring it by their freezing, by what's called the conditional emotional response. So to measure their fear, he had them responding for food on a VI schedule. And then when the tone came on, if they're afraid, if you think you're going to get shocked, what would you do? I mean, you hunker down, right? You freeze. And that's how he measured the extent to which they feared the noise. However, before he could use that measure, he had to extinguish their fear of the box. And so it's a often overlooked feature. He was a master of method. He did, I think, several hours, I forget exactly, of context extinction before he ran the crucial test. That is, he put all the rats, regardless of their experience, in the box, and they got no shocks for a long, long period of time, right? For exactly the reasons that you're raising. He needed to persuade the rats that they need not fear the box, because he wanted them back pressing that lever for the reward, which they wouldn't do very much if they feared the box, right? And only when they no longer feared the box did he sound the noise, right? And now the ones that only got shocked during the noise, when the noise came on, they hunkered down, they froze, right? Because in effect, he said, oh, what do you think about the noise? Oh, the noise, oh, great, no, the noise, it's back, right? Okay, they froze. The ones that had just as many shocks in that box, but randomly distributed in that box, once he had extinguished their fear of the box, when the noise came on, they were completely unperturbed. They went right on banging the lever for food. They didn't freeze and so on, because they were no longer afraid of the box and they were never afraid of the noise, because they had learned that the noise was irrelevant.
Thank you.
It's a wonderfully simple experiment. It's one of the greatest experiments ever done in the century in which people have studied associative learning. All right, so call it a morning or I get a day in different parts of the world there, Virginie.
Yes, that's great. That's great timing, and it's a nice mention of experiment to wrap up this round.
One thing is, I think I never got to saying, I would love it if people emailed me questions. If you think of a question, send me an email. Okay, it will help me. Take, for example, the closed form question. That's really quite an important question, as you'll see. I'm going to be pushing a theory of associative learning that is entirely closed form. And all the other theories are open form. They're all gradient descent. They're all open form, and they're all computationally very complex. So, the Rescorla-Wagner theory, for example, is a recursive. It has to be used recursively in a for loop or a while loop. It's not a closed form expression or solution to the conditioning problem. So that question about closed form is resonates in many ways, and almost all the questions that have so far been asked by people have been awesome questions. I'm not flattering you in saying that. They've really been the right kind of question that lead on to further insights. So that I really love the questions. All right. Talk to you next week.
Thank you, Randy.
My pleasure.
Thank you.
Bye-bye.
Thank you.